In this video, I want to talk about a little bit of the data associated with this lab, a little bit of the experimental part of this lab, and then I'll do an example so you can sort of see how the data gets put together. Now, the data for this lab it isn't a video, it's just some images on the document. If you made it to this video, you've already seen those images. And we'll look at the data in just a second. First off, let's just run through this reaction real quick. What are we trying to do? What are we doing? We're taking magnesium metal, and this is a solid, okay? And we're heating it up very aggressively. So a little triangle, whenever you see that, that means heat. And it's going to react with oxygen from the air and then form this magnesium oxide compound. And it's just like a white ash, really. And our goal here is to determine the empirical formula for the magnesium oxide. Now, I'm not going to spend a lot of time on the experimental part. You'll actually see the crucible and lid in the image. It's just a little ceramic bowl, little ceramic dish that can take a lot of heat. You place the magnesium in the crucible, and then you just heat it really aggressively. Let's look at the data that you generate from this experiment. And there's 3 data points, and I'll just say the first one is not a data point. You'll see the mass of the crucible and lid, and each of the images are labeled in this way. You weigh that out, the empty crucible lid. You put some magnesium in it, and then you weigh the total the total setup here of all 3 things. And this is a classic kind of way of taking a mass measurement in a laboratory. It guarantees that you haven't lost any sample in transfer, to make a long story short. And the 2 data points here, the first 2 data points, well, I mean, hopefully you can just by inspection, you can see if you subtract these 2, that's going to give you the mass of the magnesium. Now, one thing you should do before doing the lab, maybe I should have said this before, earlier, but you should watch the lecture videos on chapter 6 on how to do these calculations. I will do an example at the end of the video coming up, but I'm just going to do the front end explanation about how you take your data and then generate data for then the further calculations here. And then during the reaction, what happens is that, well, you're taking your magnesium plus the oxygen in the air, and you form this magnesium oxide. So notice that this is going to be going to have a greater mass. Right? That's actually pulling in material from the atmosphere. And then what you're going to see is that then you're going to have that data point. You're not going to have that one. So this last measurement, there it is. It's the crucible, lid, and then this compound, which again, the compound is that guy. So it'll be slightly heavier. And then what you want to do is you want to figure out the mass of the compound. Well, kind of just like we did before, you take the mass of the crucible and lid, subtract it from the mass of the crucible, lid, and compound, and then that'll give you this data point. If this is the mass of the magnesium, this is the mass of the magnesium oxide compound. Well, if I want the mass of the oxygen, the amount of sample that got brought into the system, then what I want to do is subtract these 2 values from each other. And then that'll give you your last data point. And then what you'll wind up doing is then taking the information about the magnesium and the oxygen and then doing these calculations down here. Again, I'm not going to do these calculations. I'm going to leave that up to you. Please watch the lecture videos for chapter 6, and then I'm going to do one of the calculations right now. I'm actually going to do one of the post-lab questions, so let's do that. So I'm going to do number 5 from the post-lab question. It's similar to kind of the setup that we see in the laboratory itself. We have the initial mass of the metal, we have the mass of the oxide, and so we're going to subtract these 2 to determine the mass of the oxygen, and then proceed from there with the calculations. And we're doing the same thing here. We are trying to determine the empirical formula. So let's just sort of map this one out as well. Again, we're trying to determine this X and Y. The X and Y values here, these are molar. It's really a molar ratio. So something I've said before, when in doubt, calculate the number of moles. That's practically the first step in any kind of stoichiometry calculation. So let's do that. Now we want the number of moles of the iron and the oxygen. So the mass of the iron is just given to us. To determine the mass of the oxygen, what we have to do is we have to realize that the mass of the oxide minus the mass of the iron will give us the mass of the oxygen, right? The difference there is the oxygen that's been pulled in from the air, from the atmosphere. So that's 0.96 grams of oxygen. So let's put that in here. Okay, so any mole, mass to mole calculation, you're going to divide by the molar mass of whatever you're talking about. In this case, oxygen. If I look on the periodic table, that is 16 grams per mole. So yes, the reaction took place with diatomic oxygen from the air. That's true. Once it gets incorporated into the formula here, it is no longer diatomic oxygen. It is just oxygen. So if we want to know the number of moles of just oxygen atoms in our formula, we are going to divide by the atomic mass of oxygen from the periodic table. Okay, so don't put 32 in here. This is always going to be 16, and that's going to be the same thing for the lab report as well. And then if I look on the periodic table, the molar mass of the iron is 55.85. Right? The reason why I'm dividing by this is because I want grams to cancel out. Right? That's always the goal. Cancel out what we start with and hopefully wind up with what we want. Now this one is set up pretty nicely for us. I'm going to go ahead and use the proper sig figs though. Okay, so just by inspection, we don't necessarily see the exact ratio. Okay, it's not unusual. What we want to do is divide by the smallest amount. So 0.04 is smaller than 0.06. And this comes out at 1.5, and this comes out as 1. Now, this is not unique. It may be less common, especially for our class, but it's not unusual to see a fraction showing up here. What we have to do, and there's always all these different ways to approach a problem. But if I think about, what's my X and the Y, I said these are molar ratios. These are molar values, 1 mole per 1.5 moles. Okay, so let me just sort of naively insert that into my formula and then think about what I'm looking at. This is not correct. Okay, this is not complete, I should say. I mean, this is a true statement for every 1 mole or 1 atom of iron. I do get 1.5 atoms of oxygen, but that's not the way the world works. You can't have a half atom of oxygen. So what you have to do is you need to multiply this expression by 2 all the way through, and what that does is it gets rid of that decimal there. So now this would be what? Iron 3 oxide would be the name of this compound. If you're wondering how to determine the way to calculate what this multiplier is, I want you to notice that 1.5 is 1.5. And so what you always do is you multiply by whatever is on the denominator on the bottom of the expression. Some other examples, if it was 1.3, that's equal to 1 1/3, and so then you would multiply by 3 through the entire expression. Another common one is 1.25, and that is 1 1/4, and so you would multiply by 4 all the way through the expression. And so 0.5, 0.3, 1.25 or 0.25 are the most common ones that you're going to come across. And by the way, I'm going to also use this problem as the empirical formula test review as well. Okay, so just a little heads up for you. And that's it. Thanks.